at an introduction to dynamical systems, I hope you're in the right place. So there's deep connections between resilience and dynamical systems. Many of the concepts and heuristics that we're familiar with from resilience thinking were inspired by the mathematics of dynamical systems. For example, the concept of attractors and the potential landscapes that are associated with forming cup diagrams, bifurcations and regime shifts, all these sorts of things. So the purpose of this workshop is to understand some of the mathematical background from the dynamical systems perspective behind these concepts. And in the morning session, from 10 till 12, the focus will be to be able to calculate bifurcation diagrams like the one on the right-hand side there. So more specifically, what's going to happen this morning is that I'll go through how mathematicians think about dynamical systems. One cool thing about dynamical systems is that we can quite often represent things in parallel, both in equation form and graphical form. So I'll go through some of those graphical representations, go through the concepts of invariant sets and their stability. So we'll talk about fixed points, limit cycles, maybe also strange attractors. Then, for me, this will all be building up to talking about bifurcations and bifurcation diagrams, which will then plot and simulate numerically with software that hopefully you've been able to install called XPP-Aut. And then if we have time, we'll go through some of these descriptive things to get behind this to some of the more quantitative concepts that underlie dynamical systems theory. The one I'd like to talk about is eigenvalues. So that's quite a few things. I'm not sure if we'll get through all of them by 12. If you have any questions at all, please interrupt. I'm quite happy to digress from there. So, what is a dynamical system? Let's start with that one. For mathematicians, a dynamical system consists of, first of all, a set of state variables that describe the state of a system. So all the information about the state of the system is encoded in these state variables, which might be called x, y, and z, x1, x2, x3, whatever. And then the number of these state variables is the number of dimensions of the dynamical system. So we commonly talk about, say, 2 or 3 or 4 dimensional dynamical system. So we have these state variables, and then the dynamics is encoded through a set of dynamical rules that specify how these state variables change in time. The two most common ways of writing down these dynamical rules are difference equations and differential equations. Difference equations are written in discrete time, so you take your value, say, of x at t, and you do some calculations with that to give your value at time t plus 1. The equivalent in continuous time is differential equations. These are the ones I'll be working with today. Just about all the things I'll be talking about today have a very similar form for difference equations as well as differential equations, but just for simplicity, I'll stay with differential equations today.
Sorry, so you said simplicity. Does that mean that you find difference equations more complex? Complicated?
Some of the mathematics can be slightly more tricky. So I guess difference equations themselves are easier to intuitively understand, but when you start talking about bifurcations, things are a little bit more complicated for difference equations than for differential equations. So we write down differential equations in something like dx dt equals some function of your state variables. So this means the rate at which x is changing at the current time depends on the function that we calculate on the right-hand side. So one way of writing down this derivative is dx dt, another one is x dot. And then, of course, in practice, we usually use these dynamical systems as a model for the dynamics of a real world system. So here, when we say dynamical system, we often refer to the actual real world thing which is changing in time. But for the purposes of the mathematics and for the purposes of today's seminar, when I say dynamical system, I'm talking about the mathematical object. So we can talk about solving the dynamical system where it might be harder to calculate a reliable solution of the actual real world object. So speaking of which, when we talk about solving a dynamical system, what we mean is that we need to start from a set of initial conditions. So we specify the time when we're starting, and we give initial conditions to all the state variables. So for example, we start at time t equals 0, we specify the values of those state variables at time t equals 0. We then apply the dynamical rules, whether those be the difference equations or the differential equations, and then we obtain what's called a trajectory, which consists of the values of these state variables over time. And this can be done analytically in some special cases, but almost always it's done numerically. And then once we have these trajectories, we can plot them in a few different ways. One of the most convenient ways is in what's called a phase space or state space diagram. The full state space or phase space is the space of all possible values of the state variables. So we construct a space where all the axes are the different state variables. Obviously, it's easiest to visualize when we have, say, just two state variables, because then we'd have just x and y. In theory, the state space is an object which can work for any number of dimensions. But usually when we plot them, we're going to project it down to a small number of dimensions. So let's start playing straight away with some state space plots. We're going to use two models during this morning session, which we're going to simulate on XPP. The first one is one that should be very familiar to any ecologists here. It's the Lotka-Volterra model. The Lotka-Volterra, or the most basic version of the Lotka-Volterra model, has two state variables. We have a population of a prey species, which we will call X, and a population of a predator species, which we'll call Y. So we have two state variables, X and Y. And then the rules, which we write down in terms of a differential equation, are going to be these two here. So the population of the prey changes in time according to a primary production function, and then also, so it increases due to a primary production function and is decreased by a predation process. And then we have the population of the predator, which is increased by its predation on the prey and is decreased by mortality. So what we're going to do for the Lotka-Volterra equation, I'm going to I've specified here some values for those parameters, alpha, beta, delta, and gamma. And I've also specified in the problem some initial conditions. First thing I want to do to explore these different graphical representations is first of all plot by hand the right-hand side of this function at the top. And then we're going to use XPP to plot some time series of X and Y, and then also plot the state space. So this is just to get you familiar with some different ways of representing what's going on here. So the first one is pretty straightforward. We want to plot so the intercept here is going to be a x, and this goes down like that. So this is one plot we can make. The important point, and I think I've actually missed a slide here where I wanted to explain all this. The important point is that we have a lot of different plots that we want to make, so we have to always pay attention to what are on the axes. In this case, we're just making a plot of this function. So we have y on one axis and f of y on the other. This plot is just representing what is going on in that first equation up there. So that's straightforward, that's one plot. Let's get on to a couple of other plots. So now we want to solve this dynamical system, this pair of differential equations, to produce some time series of x and y. We're going to do this using XPP. So those of you who have it installed can follow along with me. Those who weren't able to get it working, just watch for the moment. We'll have a break around 11. And if you want help installing it, I can try to help you then. So if you're on Windows, you need to run xmin. There it is. And we're going to run XPP. So the file we need to open is the lotkavolterra.ode that I sent around to you in the email. The easiest way of opening it is just to find wherever it is and then drag it on, drag the file onto xpp.bat. So you'll get some stuff at the command prompt, but hopefully you'll also get this nice little display open for you.
Sorry?
Yesterday I missed that window. Now
I couldn't even select the file.
So we can try to work through that in the break. Okay. But actually, I also wanted to show you what this file looks like. It's a very simple text file. This is the file that XPP takes as an input, and it specifies the dynamical system that we want to solve. So the way we enter information for XPP to understand is that we have here written down the differential equations that we want to solve. The par keyword tells us that these variables are parameters, and we can set initial values to them here. We don't have to. We can also do that inside XPP, but I'm going to set some values to them here. And we can also set in this file, we don't have to, but here I've set some initial values to these state variables as well. One important thing with XPP, one quite bizarre thing, is that it doesn't like spaces very much. If you put a space in here, it won't open, it won't run the file. Yes?
Is it possible to use MATLAB or Julia instead?
So you can definitely use MATLAB to solve differential equations. What we're going to use XPP for a little bit later on is to calculate bifurcation diagrams. This is a lot harder to do in other software. XPP is sort of designed to do this. As I'll mention later on, there is an add-on for MATLAB that you can use, but I prefer XPP. So that's the ODE file. The order of the definitions doesn't matter. You can put the differential equations first and then the parameters afterwards, whatever. But I think it does pay attention to case, and as I said, the spaces after the commas does matter. You don't want any spaces, or it doesn't want any spaces.
Can I?
Yes.
Good question. If you want to write comments, what do you?
Hash.
Hash.
Yep. You'll see that in the next file, actually. So to solve this little exercise that I had before, I produced one type of plot there for you. For the next plot, we want to produce some time series for the solution of this dynamical system. So we've opened XPP. Just to get you familiar with this screen, it's fairly intuitive, but you have options here for your menu on the left-hand side. You can use the mouse, or you can just use the keyboard to press the letter that's capitalized. So U will get you numerics, for example, P will get you parameters. You can also click on these little buttons up the top here, which will give you another little window where you can enter your initial conditions, or your boundary conditions if you're doing partial differential equations. The most useful other one is probably the parameter window, where you can change your parameters. But anyway, I've already set the initial conditions and the parameters in the ODE file, so we don't need to put them in here. So we now just do initial conditions, click on initial conditions, and then click on, I said run, it should actually be go. Let's click on go. So this is outside the window that we have. The easiest way to change the window is to go window and then fit. And now we have very easily a nice beautiful plot of the characteristic oscillations of the Lotka-Volterra equations in XPP. It's plotting now x versus time. If we want to produce a plot of y, there's a few different ways of doing it, but the easiest way is to click on this one, xi versus t, and change it to y. Lowercase or uppercase doesn't matter. And then we get y as a function of time. Okay, so this is a second type of plot we can make, a second graphical representation. These are time series, plots of a state variable over time. For the third variety that I wanted to plot some state space diagrams, which is one state variable against another state variable. We can also do this in XPP. We want to go to view axes here, 2D. Now we want to make a state space plot, so we'll put x on the x-axis, y on the y-axis, and go from 0 up to 3 on both x and y. We could also add some labels if you like. So that was under, this command was under view axes and then 2D. Now we have the state space plot. So time is implicit in this diagram. This curve is created by running time forward and then seeing what x and y do, making a point at each value of time, and this is the trajectory of how the system moves in state space over time. Okay, any questions about this example before we go on? Yes, Nanda?
I don't know whether it fits the scope, but I have a question about the dynamical systems theory. What does it mean to solve a system? Because you gave an example of this model, and that it could represent a real-world system like a predator-prey, but is it always a predator-prey, or could it represent more? And if you have a description of that, what are we solving? I mean, I understand that we solve the formula, but what does that represent? What's the goal of solving that?
So solve, in the case I'm using it here, means to figure out how the system changes over time. How the system, so given some initial conditions and the functions that make up the dynamical system, we're solving it to see how the thing is going to change in time.
Under what conditions?
Yeah, and then what you'd want to do with those solutions is investigate how those solutions change there's, I guess, a whole raft of questions that you could then investigate. How they change, how these solutions change depending on your parameters, depending on your functions, depending on adding extra processes, things like that.
And then, if you can show the formula again, could you point out to me what are the state variables?
Sure. So here, the state variables, let's make this full screen again. State variables here are x and y.
Okay.
We have two state variables, x and y. So the values of these two quantities, x and y, characterize the state of the system at any given time.
So that's two functions to this, as a part of describing the whole real-world system.
So yes, in converting from the real world into this model, we've assumed that these two quantities are the only things that are important.
Okay.
So x and y state variables. I never actually defined this before, but I refer to alpha, beta, gamma, and delta, which are these constants, as parameters. They're usually called parameters in dynamical systems. Could
And
also-
the initial conditions, how would you, which are these the constants?
No, initial conditions I haven't written on this slide. I wrote here. So in this example, I set the initial condition of x, which I indicated by x at time 0.
Yeah.
I gave that the value 2, and I've written y at time 0 to take the value 2.
So the initial conditions relate to the state variable.
Exactly. Yep. Good question. Any other questions? Yes, Emily.
Is it only the functions from the start and initial conditions that you start? Can you insert the basic system over time and can you change the functions during the process?
Can you change the functions?
Not the so for example, can you change the alpha after like 100?
Okay. Yes. Certainly, computationally, in XPP, I think you can probably do it in XPP. I think it's possible to set up functions that are dependent on time, or parameters that are dependent on time, and then feed that into the rest of the equations. In terms of analysing it mathematically, mathematicians generally try to avoid making things time dependent, explicitly time dependent. There's actually a word which escapes my mind just now for describing the difference when you have time explicitly in the equation and when you don't. So yes, certainly from a computational point of view, you could define these parameters to be time dependent. That would be fine, but it would complicate the mathematical analysis, the bifurcations and so on, that we're going to do in a moment. The concept of bifurcation wouldn't really apply anymore, because that really only applies to a dynamical system which is consistent in its structure, not where the parameters are changing. A good question. Any other questions? Yes?
The state space diagram you just plotted is
Yes.
still only valid for those initial conditions.
Exactly. That's a good question. We can, let's see if we can do it here. We can get other initial conditions. Let's try this by going initial conditions, mice. So initial conditions, mice. Just move that little box out of the way. And then just click somewhere on the state space. We can generate additional trajectories in the state space. The Lotka-Volterra equations are a little bit unusual in the sense that they are conservative equations. Normally when you do plots like this, you'll end up with all the trajectories coming together at one invariant set, as I'll introduce later, one fixed point or one stable cycle. In most realistic simulations, you aren't going to get this cascade of orbits like we have here. But yes, that was a very good question. So each...
when choosing now with your mouse the initial conditions, can you see what they are?
What values they are?
Yeah. Because now that seems a bit random now. Just click somewhere and then but you don't know which parameters.
So that was the graphical way of doing it. The other way, so we press escape to get out of that version there. If you want to put in specific initial conditions, what you can just do is go back to, oops, not parameters. Well, there are a few different options actually in XBP. You can go to this option here and type in your initial conditions there directly. So let's try that. Let's start with 2.5. 2.5. Okay, and close. And then we do initial conditions go to run those parameters. And then you get another one in there. You can also use, I think you can use this funky thing down the bottom. No, that doesn't do initial conditions, that just does parameters. But if you have a parameter you want to vary, like alpha, you can also use this little thing down the bottom here to vary parameters and see how the shape of your solution changes as you change that parameter, which is pretty cool. So I got that by clicking on this little box here. To get this window, I entered the name of my parameter. One of my parameters is called alpha. You can set it to whatever value to start off you like. Set the range over which you want this slider to go. And then click OK. And then you can just use the mouse to change this slider up and down and see how the shape of your solution changes. So it's got some quite handy little features for exploring your dynamical system. And we haven't even got to the coolest part yet.
No.
But before we get there, any other questions?
How do you plot +2 dimensions?
More than 2 dimensions.
Yeah, or is it not common?
I think this can do 3 dimensions. Not using that one. Whoops. Scroll down. Well, this system only has 2 state variables anyway, so we can only do 2. It has a limited capacity to do 3-dimensional plots. My brain certainly can't visualize 4 dimensions. So you're just choosing a subset of those state variables to plot. So.
Because is it common that a dynamical system description or functions have 2 state variables, or what is common? 3, 4, 10?
Depends on what you're using them for. I mean, so if we're in the business of constructing stylized models, then usually we want them to have quite a low number of state variables, like 2, 3, or 4, something like that. If you get to a system that's a bit more complicated, 10, 20, you could call food web models a type of dynamical system. you could construct a food-web model with 10 or 20 state variables, or even you could construct a dynamical system with hundreds of state variables. But in that case, I'm not sure you'd be using XPP. Okay, so let's go on. Okay, so we have this state space, and I've copied down the bottom there one of the plots from the little Lotka-Volterra simulation. What points in the state space of a dynamical system are special that we want to pay particular attention to? One type of important point are those that are invariant sets. This is the mathematical term for a group of points that, under the rules of the dynamical system, does not change over time. So that if you start at an invariant set, you stay within the invariant set for all times into the future. There are two types of invariant sets that we'll pay attention to today. The first one is fixed points. This is a pretty obvious type of invariant set. If you start at the fixed point and then run your system into the future, then you will stay at the fixed point. And where there are there are a few types of fixed points. Two interesting ones are stable and unstable. Stable is where, obviously, in the neighbourhood of the fixed point, you will, as you go towards the future, be drawn towards the fixed point. And then the unstable one is if you perturb yourself away from the fixed point, you will run away from the fixed point into the future. So they're fixed points. And the other one is limit cycle. A limit cycle is basically the mathematical word for a stable oscillation. So it's where you have a periodic solution to your dynamical system. And if you start on this limit cycle, go forward in time, you'll go around the limit cycle, around your oscillation in state space, and then back to where you started, and continue going around this loop forever and ever. You can also have stable and unstable limit cycles, where if you shift yourself off the limit cycle a little bit, and then if you run into the future, your solution will come back onto the stable limit cycle. And in the other way, if you perturb yourself off the limit cycle a little bit, an unstable limit cycle is one where your solution will run away from the limit cycle to the future.
Question.
Yes?
Those notions related with the positive and negative feedbacks have nothing to do with it's running away, they're converging towards it.
That's an interesting point, that dynamical systems theory doesn't pay as much attention to feedbacks as systems dynamics does. I'll get onto a little bit this afternoon, the difference between dynamical systems and systems dynamics, which is bigger than you might think. So yes, obviously, if we want to think of it in terms of feedbacks, there are obviously feedbacks, positive feedbacks which are making the system stable, unstable, negative feedbacks which are making the system stable. But these are the concepts which are not often discussed in dynamical systems. We just go directly to eigenvalues, actually, as much as the stability. Yes?
Regarding the stable and unstables, so the fixed point is regarding the perturbations. Whatever the perturbations will still lead to that one fixed point or away from that one fixed point? Or is it like fixed point in the terms of like for that set of parameters at any given initial condition you will lead to that fixed point?
No, so it's not. So in terms of parameters and initial conditions, you only talk about a fixed point for a particular combination of parameters. Fixed points, and this is that concept of a bifurcation actually. Fixed points can change their nature. They can go from stable to unstable, or they can disappear when you change parameters.
I was thinking about the logistics model and the logistic map
Yep.
specifically. And in that case, you have like a parabola and you just converge to one fixed point, whatever the initial conditions for S would be, for example.
So yes, that's another one. So with the initial conditions, a stable fixed point does not need to be attracting for all initial conditions in a state space.
You can have several.
The concept of this, if you want to add a few more words to this concept of stability, what we're actually dealing with is asymptotic local stability. So asymptotic means that it is stable all the way into the future as time goes to infinity. Local means that it just needs to attract the points in its neighbourhood. So that if you are at the fixed point, if you are at a stable fixed point and you perturb your position by a very small amount, but which is greater than 0, you will end up being attracted back towards that fixed point. Good question. So yeah, it's only a local concept that we're dealing with here. Let's go on. So, different graphical representations of dynamical systems. I mentioned that it's one good feature of dynamical systems is that we can represent things both using equations and also in graphical form. I showed you we've gone through a few graphical representations already. One type of representation we can make is just the shape of a function that appears on the right-hand side. This is what I tried to do here. Another representation is time series, where we plot a state variable as it changes over time. Another thing we can do is state space, where we plot two state variables against each other and then map how the system goes over time. Two more that I'm going to get to, actually first the last one and then the second last one, we'll get